All right, so let's do one example. Okay, so two ways to create or to build a cross section could be, let's see, we have an I section. So I build the I section as doing the top piece, and you can attach it to a lower piece over here. Okay, so the first way to do it would be to put, if you want, you can put a nail or a bolt over here, another one, let's say over here, and the spacing here would be S, and then dimensions for the cross section will be, this would be 1/2 inch. This would be 1 inch, the thickness of the web. This would be 4 inches, and the base or the flange will have a width of 3 inches. Okay, and let's say both these two are subjected to a shear force V that I put over here, which will be what we need to find. Okay, so this will be the first way to build the I cross section. The other way would be just to have a vertical one. I'm gonna go one more here and one more here. All right, and to have here the other pieces. Okay, so basically this time we'll be putting the nails. One, this could be the other one, this could be one, this could be the other one. Oh, forgot to do this, this. All right, so here we can have another one. Back here. Here. And S will be the spacing. Okay, so this will be here. Case A. Case B. And here what we know is that so knowing that, let's say S equal to 9 inches, so this is the spacing between the nails or the bolts, and the shear force of the nail, I just call it V sub N, is 40 pound-force. So basically that means that the force you can apply to the nail in order to break it is 40 pound-force. So we need to determine which cross section, I mean, which cross section build up will resist the higher shear force. Okay, and we can just today kind of discuss it. Let's say if the force is vertical, in here the force will be in the direction of the nails, but in this case will be perpendicular, no? So we finish the class saying that if we use our common sense, will be this one should resist a higher shear force D. Okay. So what we need to do again, everything is to apply the equation here. So the equation that we'll be using is tau equal VQ over IT. Okay, so V is what we need to find. So we need to find I and Q, basically, no? So let's start by I. So here, I'm gonna go a bit faster. So let's see if we have here. Our cross section. The I about the neutral axis will be equal to what? So this is we know the neutral axis will be in the middle. So the way I do it is this way, okay? So since it's symmetric, what I'm going to do, I'm going to consider this as being a whole rectangle. All right. And then I'm going to remove the moment of inertia created by the two shaded areas over here, this one and this one. Okay. So we do that. Let's see what was the base. It was 3 inches. If the thickness of each one was, so the total one, this is 0.5, 0.5, and 4 over here. So let's see. What will we have? We'll have 1/12 of the base, which is 3 times 5 cubed, will be the whole rectangular cross section, minus, now I'm going to remove these 2 little pieces over here. Okay, so that will be what? 1/12 of, this will be, so what will you over here will be, so this is 3. This is 1, so that will be 2. So each one will be 1. And the height will be 4. So if you do this calculation, you get that the sudden moment of inertia is equal to 20.58 inch to the 4th. Okay, so let me repeat. This one will be of the whole rectangle. This will be the 2 little pieces. Okay, these ones are here. All right. Okay, and this will be the same one for case A and B. Okay. All right, so, maybe let me put over here, since I put here equations, What is the other equation that we have seen is the shear flow is equal to the shear times T. Okay. So we're gonna see what happens next. So let's say we combine the two equations. So we call in the two equations, tau equal VQ over IT and Q equal tau over T. Okay, and we have the third equation. The spacing is equal to the V of the nail divided by the shear flow. Okay, so combining above equations, let's see what we can do. So let's start maybe by Q equal to shear stress times the thickness. So we replace the shear stress by VQ divided by IT times T. So this will give us that Q is equal to V times Q over I. Okay, next we have the equation S equal V nail over Q, which will give you that S equal to V nail divided by V times Q divided by I. Which this will give V, if I solve, will be equal to what? V nail times the moment of inertia divided by, so V divided by QS. Okay, so here let's make sure that we understand every single term. So V is the unknown we're trying to find, which is what? Shear force resisted by cross section. What is Vn? Is the shear force resisted by nail. So it's two different ones, okay? I is N sub A for us is cross section, second moment of inertia, Q will be the first moment of inertia. And S is the spacing between nails. Okay, so in our problem, what do we know? We know V nail is 40. We know I, neutral axis, we just calculated to be equal to 20.58 inch to the fourth. And we know the spacing, in this case is given to us, is 9 inches. So in order to find V, what do we need to find? Q, all right? And Q is always a problem. All right, so let me go to the next page in order to find Q. So next page. So obviously you see there's a difference between building the cross section this way or this way, no? So what is the term which is going to show you the difference? Is going to be the Q. All right, so let's go to case A. So what is case A? I just redo the figure again. This. Okay, and we are attaching this way. This is 3 inches. Okay, I'm not going to put too many dimensions. This is whatever, 4 inches. Most important is where I'm going to put the neutral axis. Okay, so in this case, what would be the area that will break the nail? What would be the area that the nail will be withstanding? Will be this one over here, no? The force will be perpendicular over here. So what we need to find is the Q of this section here. Let's say it will be Q sub A. Okay, so if you remember, what did we say? Q sub A will be equal to YdA, which is approximated by the area times distance from neutral axis to CG of area. So this gives you what? What is the value of the area? The area is 3 times 0.5. Now, what would be the distance from the neutral axis to the CG, which would be somewhere over here, so in the middle here. So it will be that distance over here. What will be that distance? That will be 2 plus half of 0.5, no? So it should be 2.25. And if we do this calculation, you get that Q sub A is equal to 3.375 inches. Okay, so recalling this equation here, we have that V, so that we'll have that V for case A will be equal to V Nel times I of the neutral axis divided by Q sub A times S. So if we do the numerical application, this gives you V sub A equal to 40 times 20.58 divided by 3.375 times 9. And this gives you that the shear force that can be resisted in case A is 27.1 pounds. Okay. So now we're going to go to another page. We're going to do the same thing for case B. And again, I'm just going to redo the figure. Okay, will be the same dimension. So this is 3 inches. This is 0.5. And this is 1. I mean, I don't know how much we need here. This will be 1. And this will be here basically 2 and 2. Okay, so basically here, what do we have? V, we took this area because this is the one that is perpendicular to the nail, no? This will be the area that will be holding the nail. In this case, oops, where is it? In this case, what will be the area holding the nail? Will be this one over here. So then, see what did I put on the one? Yeah, so this is Q sub A, so this will be Q sub B. So again, I'm gonna rewrite everything. Q sub B will be equal to Y dA, which would be equal to the area times the Y bar, which would be the neutral axis to the CG. So what would be the area of that little piece? Will be 1 times 0.5. And now what is that distance here from the CG to the neutral axis will be 2. I mean, the same as before, will be 2 plus half of 0.5. So 2 times 25. So this is going to give us that Q sub B is equal to 1.125 inch cube. So finally, as before, let's use this equation here that we had to find the shear force, but for the case B. So VB will be equal to VNL times I neutral axis divided by Q sub B times the spacing. So this is equal to 40 times 20.58 divided by 1.125 times 9, which give you that VB equal to 81.3 lb. So conclusion is very simple. VA much large, sorry, VB much bigger than VA, meaning that case B more efficient method to build up cross section. Okay, so obviously this is just one design parameter, but if you think about it, you know, maybe at the end of the day, let's say you make calculations, you find out that actually your shear force that you need to withstand, and the real case, let's say is, so for this one we have 81.3, on the case we had 27.11. Let's say it's only 10 pounds force, okay, that you need to resist. Then maybe what do you need to take into consideration? Which one is really easier to build? Case A or case B? Case A, no? It's a lot easier, less cuts, no, to do. And then how many nails are you going to need? Half the amount of nails, no? So you see, it's not only one consideration, no, when you do a design. Doesn't mean that this one is bad all the time, no? Maybe if the margin of safety is so large for the value V, you can go and just build it that way. Okay? All right, then I don't know. Then what could be another decision you can make? Maybe you want to optimize, maybe you can change the spacing, no? Maybe you want to say, okay, I want to still use this construction, but I want to make it a bigger safety. So what can you do? You can actually reduce the spacing, no? You can put more nails, and then what will happen if you look at the equation? The force will be divided by 2, no? Yeah? Okay, so. No, so if you put more nails, this will be lower. So the V force will be multiplied by 2, sorry. Okay? Because this will be reduced, no? Instead of being 9 inches, will be 4.5. So we mean that this value will be multiplied by 2. Okay, so what I mean is that it's not only one answer, depends on your design, whatever you want to achieve. Okay, so example. All right, so let's see. Over here, it looks like there is a beam. Oh, pretty complicated the way I sketch it. Okay, I'm not going to do it as I sketch it here. I'm going to do it differently. So there is a beam over here. Which is 400 millimeters long and has a force here of 13 kilonewtons and a lateral force over here of 9 kilonewtons. So let's select here a reference frame. So you want me to use the one I use here on my notes, or you want to select? I don't care. I mean, tell me how you want to use it. So let's use Y, this one. Now the question is which one which one you want to be X and Z. You want X to be this direction, or you want to be the length of the beam? Okay, so X, Y, Z we have. So then we could say that what? This will be then F of Z will be equal to minus 9 kilonewtons. And this will mean F of Y equal to minus 13 kilonewtons. All right, and here this is fixed. So now the cross section is an I-beam where let's see, this length over here looks like it's going to be 150 millimeters. The height of the beam is, so it's not at all to the scale, is 75 millimeters. And the thickness of all of them T is 13 millimeters. And the question here, so imagine you have a point, okay. Imagine you have a point A, it's right where I put the T. Okay, so let's say here, the question is to determine the normal and shear stress at points A and B. Now I'm gonna have to do here the figure. I don't want to put too much on the same figure. So point A is right here. So it's at the corner. And point B is located at 60 millimeters of point A. And let's see if we want to be accurate. What should be here the coordinate system? This should be X and Y. Yeah, okay.
I think it's Y.
Oh, yeah, sorry. Yeah, I was looking at it. So this should be YZ, absolutely correct. So Y, and actually the Z should be on the opposite direction. You see, it's because I changed from the one on the notes. Thank you, thank you. No, you're right. So now should be Y, should be YZ. Okay, under this form over here. Okay, so here, let's be careful, but before we even start the problem, let's try to do some thinking, okay? Let's think about this cross section. Let's first look at the force here. Let's just say we calculate here what's happening to the force in the Y direction, the one going up and down. What would be the shear stress upon A and B? What should it be? Should be 0. Yeah? Just due to this force. Is it anything to rub over here against? Nothing. Now be careful. If we look at the force Fz, now would the shear be 0 at A and B? No, it will not be 0, no? Okay, so again, the strategy in all these problems is we're going to find first the moment of inertia, and then probably we're going to find the normal stresses just due to one of the forces, and then just due to the other one, no? Okay, so we're going to break the problem into this load and then this load, and we'll see what's happening. All right, so first thing we're going to do is to find the cross section. And then I don't know if I did in much detail. Yeah, okay. Yeah, let's do it that way, okay? I was just thinking that maybe the appropriate way would be to do what? First do the free body diagram, then find the reactions, okay? But let's first just do the cross section. So the cross section properties. So this one, I'm going to stop giving that many details. So here, because we have, this is going to bend in what direction? If we only look at the Fy, this is going to bend about the Z, no? Okay, which means that we need to find I sub Z. So I'm going to start going faster. I'm going to do it as before. I'm going to take the whole cross section here, all of it. So this will be equal to what? 1/12 times 0.15 meters will be the base, times the height will be what? 0.075 meters cubed. And now I'm going to remove the moment of inertia of the two little pieces over here. This one and this one over here would be 1/12 of what would be the base. So you will have 150 minus 13 divided by 2, which if my notes are correct, this should give you 68.5, which would be 0.0685 times what? 13 plus 13 will be 26. 26 minus 75 49 0.049, and this should be to the cube. Okay, so this will give us an I sub z of 3.9303 10 to the minus 6 meters to the fourth. Okay, now because we have the force of the Fy, we need to find I sub z. Now, because we have a force on the z, what do we need to find? It's going to bend about the y. Okay, we need to find I sub y. So if we do the same thing, what would you get? If we do the center piece, but now everything will get reversed, you will have what? 1/12 of the base will be 0.049 times so will be this times, okay, will be T, which is 13 millimeters, will be 0.013. So it's this here, 0.049 times the thickness. We go in that direction. Plus now we're going to do the moment of the top and the bottom piece. So that would be what? 1/12. What would be the base? Would be the thickness, 0.013. And what would be the height? Would be the 150 millimeters, which is 0.15 meters to the cube. And if you do this calculation, we're going to get I of y equal to 7.3215 10 to the minus 6 meters to the fourth. All right, so okay, and then we're gonna have a bunch of reactions. We're gonna have so let's be careful here, because let's remember the coordinate system. So this is X, Y, and Z. So we're gonna have here a moment, a resistive moment, M sub Y, and so let's see, it should be, let's do it this way, and a resistive moment M sub Z. Maybe I should do this, M sub Z. Then here we're gonna have an A sub Y, A sub Z, and we're not gonna have an A sub X, so I'm not gonna put it. It's just gonna confuse everything. And this is 0.4 meters. So in order to find the reactions, we need to do the summation of forces. So we're first going to do the summation of forces on the Y. Which will give us what? AY minus 13 equal to 0, which means that AY will be equal to 13 kilonewtons. We do then the summation of forces on the Z. I mean, you see that I'm not doing Fx because it will be 0, no? I don't want to add too many things. So this will give you what? AZ minus 9 equal to 0, meaning that AZ will be equal to 9 kilonewtons. Okay, now we need to be a bit careful. Next thing we're going to do is take the moments about Z. So it's the moment about Z, but at point A. So it will be the origin. Counterclockwise positive. So what's that going to give us? M sub Z. What is creating the moment about the Z? Is the 13 kilonewtons times the 0.4 meters. Will that one be positive or negative? That one will be creating a, let's see, let me reverse it. Counterclockwise, no? So minus, sorry, would be minus here. So mz minus this equal to 0. So we'll have m of z equal to 5.2 kilonewtons per meter. Let's check the sign for a second. So this is going to create a moment going down, and this should be going up to counter-react it. Okay, so which is the direction that I did. So okay, that's correct. And now we need to find the moment about the y. So we need to take the moment here equation about the y at point A, and we do the same thing. Which will give you what? My. Then the moment created by the 9 will be, so this one here I did a mistake, okay? I mean, this is the way here I plotted what I plotted here clockwise, no? In order to be positive, it doesn't matter really, but generally we say that counterclockwise is positive. So this will be positive. Now this would create a clockwise moment, so it will be minus 9 times 0.4 equal to 0, which will give you that the moment my equal to 3.6 kilonewtons per meter. Okay, in this case, we can save a lot of work, to tell the truth, if we are a little bit smart, but maybe I'm going to do it. Let's go back to the initial problem. So, oh, I forgot to mention something. So where is point A and point B? This point A and point B will be located at fixed end. So basically, what does that mean? They will be at this location here. So this will be at x equal to 0. I mean, let's do the whole procedure, okay? So what I was trying to say is that do we need to calculate the shear and bending moment diagrams at the root, or do we know their value? What did we just discuss about the homework problem? The value of the shear should be equal to the value of the reactions, no? And the value of the moments will be equal to the value of the reacting moments. Okay, so really you don't need to find the shear and bending moment diagram, shear and bending moment diagrams, but let's just do it as an exercise. Okay, so reactions, and now we're gonna find here, but I'm gonna go a little bit faster, shear and bending moment. Okay, so first I'm gonna break this in two parts, otherwise figures are gonna be way too complicated. So let's first look at the y z-plane. So what does that mean? Which load am I looking at? On the y z-plane, you will have what? You will have the a sub y that we calculated to be equal to 13. So on this plane, this is going to bend about the, so we look at AY is this one, we look about the Z. So we have the moment about the Z. MZ here, but we need to be careful because, okay, it's positive, so 5.2, that's fine. Okay, and here we're gonna have V on that plane. We're gonna have here M. So let's see, that will be what? Vy. That will be M bending Z, okay? Let's call this one M bending Z. Again, we don't need it, but oh no, okay. So if I apply to this figure over here, summation of forces on the y equal to 0, this will give us that AY minus Vy equals 0, which will give you that Vy is equal to 13 kilonewtons. And if we apply the moment equation about the cut, this will give MBZ plus the MZ that was plus 5.2. I'm gonna start putting values. And now this force over here is creating a moment of what? A positive, a clockwise, so will be a negative moment of 13x equal to 0, which will give you that bending moment Z will be equal to 13x minus 5.2. Again, all this is not needed, but I just do it as a review. So if we go and plot the shear and bending moments, we should have what? This would be equal to constant 13 now. The moment is a linear function that will go from what? From minus 52. And if we do 13 times 4 is 52, no? So this is 5.2, not 52, it's 5.2. So be careful, it's 0.5.2, so we get 5.2. So we go from here to 0. Okay, this should be a straight line, okay? All right, so now I only have one page left, so I don't know if I'm gonna have space to finish. We do exactly the same thing. Yeah, last page. So 52, see if I have space to finish this. We follow exactly the same procedure, but this time instead of for the YZ plane, YZ plane, we're gonna have to look at the X Z plane, no? Because this will be curving this in that direction will be so ZX plane or XZ plane. This time the figure will be follow exactly try to follow the same step as before. I do this figure over here. So this would be the cut. So we need to be careful here with this. So it would be X. No, I don't want to put X here, okay? Forget about this X. Otherwise, I'm gonna have to do it sideways. Now, what I want to put here is, so we had A, Z. Can I do this one? Let's put X, Z. Maybe that could work. So let's see, what do we find for AZ? AZ was equal to 9 kilonewtons, so AC is like this. Then MZ is MY. Sorry, we need to look at the MY, not the MZ. So X. So the X will be in that direction. Sorry for that. So forget about the MZ. There's no MZ. We need to look at the MY. The MY is 3.6. And here we'll be looking at BZ and MBY. I know it becomes complicated, that figure. But eliminate the MC that I did. I want to finish on time. We will do summation of forces on the Z equal to 0. So this will give us that 9 minus F of Z equals 0, or F of Z equal 9. Kilonewtons. You do summation of moments about the cut equal to 0. This will give you M by plus 3.6 minus 9x equal to 0, which will give you MBY equal to 9x minus 3.6. So again, if we needed to plot the shear and bending moment diagram, we'll get here 9. And for the bending moment, negative 3.6. And 0. So it would be VZ and BY. And what do we have in the previous figure? I don't know anymore. This one would be VY and BZ. Okay. And we stop over here. But again, all this stuff